Yeah, so I think you have to, oh,
Okay, so this is for you 1 more minute. I mean, we're not going to fall behind schedule because
So
I
are
think
you
we
recording?
have exactly 1 minute of things to say.
oh, what happened?
Oh, I think maybe what happened? Oh, that's pretty good.
Okay.
I guess it means you have to touch it periodically.
Now it's not sharing anymore. What's that? Now it's not sharing the slides anymore. Ah, now it's back. Okay.
Yeah.
It's done.
Done, yeah.
It's okay?
Yep. Okay.
Hang on, because I see we have our chairperson, so it means we can start. Let's just give it 1 more minute. How many people online? It's
Like 769.
69? Oh, okay. Oh, yes. Okay. Okay, then I guess we could get started.
When more people are coming.
Yeah, so just 1 more minute.
We were
People from California
as well. Oh, but we went through Hollywood because somehow Google Maps can just go through Hollywood.
Yeah, something Google Maps was like rerouted us the whole time.
Okay.
Yeah.
There's like
So-
in and out.
So we could get started. So unfortunately, we have to run a tight schedule because of our European friends. We don't want to keep them up too late. So I'd like to welcome everybody to the Baumick Institute and IPAM, except virtually, of course. Of course, I apologize for the pandemic. But hopefully next year, we actually are going to meet a person somewhere. So this year, what we did, we included a new topic. So there'll be on the EFT bounds. So we'll have our first speaker, David Simmon-Duffin, who will say a few things about that, and then the rest of the day will be talks about that. And an unfortunate side effect of that is that, of course, we have fewer slots about the normal topics, but we thought that it would be good to have new topics. That's always good for a conference. And we'll also have many student talks. The SAGEX collaboration has been quite good in funding students. So there are quite a few students graduating. Their talks will tend to be towards the end of the day on Tuesday to Friday. I encourage people to come and those talks and welcome new people to the field. So I guess without further ado, Mikkel is going to be our chairperson and get started.
Okay, yeah, so let's just get into it. First speaker of the conference is David Simmon-Duffin, and he's going to talk about dispersive bounds and gravitational EFTs.
Okay, thanks a lot. It's great to be here. This is my first physics trip in about 2 years. Okay, so I was asked to give a review talk about dispersive bounds on EFTs. And this is already becoming a pretty big subject, and we're going to have lots of talks about it today. So this is not going to be a very complete review. What I want to do is talk about some of the basic questions, some of the physical assumptions that go into these kinds of computations, and mention some comments about open questions that I think are interesting to think about for this conference. So the central question that we want to answer is which effective field theories can be UV completed. And it's been known for a long time that not anything goes. And a classic example of this is the result by this group in 2006. So they considered an effective field theory of a scalar that's weakly coupled at low energies. You can look at the amplitude for scalar scattering, 2 to 2 scalar scattering, and it has some kind of low energy expansion with various terms that correspond to irrelevant operators in the effective Lagrangian. And they pointed out that there are positivity conditions on these Wilson coefficients. So for example, G2 has to be positive, and that's a consequence of causality and unitarity. And they gave two kinds of arguments. One was based on causality in some non-trivial background. And there's another argument based on dispersion relations. And recently there's been a flurry of work extending and generalizing these types of dispersive arguments. And so that's what I'm going to focus on in this talk. And the upshot of this recent work is that you can derive sharp bounds on these Wilson coefficients, sharp two-sided bounds on Wilson coefficients. And these bounds have the scaling expected for dimensional analysis. So the framework is, you imagine you have some low energy effective field theory. There are some unknown states at high energy, and those unknown states start at some energy capital M. So capital M is like the UV cutoff for the effective field theory. And the claim is that you can derive sharp bounds on the Wilson coefficients in terms of this UV cutoff, capital M, that scale as you would expect from dimensional analysis, and furthermore have clear numerical coefficients. So the slogan is that dimensional analysis is a theorem in this case, not just an expectation. So what I'm going to do in this talk is I'll review the techniques that go into these bounds. And I want to focus on some of the physical assumptions that go into them, because there's some interesting discussions that we should have about these physical assumptions. And then I'll talk about technical tools for dealing with the case of gravity, which is what we're all interested in this conference. And so that's the plan for the talk. Are there any questions before I get started? Okay. So let's talk about dispersion relations. So there are three basic assumptions that go into writing down dispersion relations: analyticity, unitarity, and Regge boundedness. And so I'll talk about each one. So here's an example of a type of analyticity assumption you might want to make about your amplitude. And I should say that we'll have other talks today that make different kinds of assumptions about the amplitude, but this is a simple framework that we'll take. And the assumption here is that the amplitude has some low energy region here in blue. And we're just going to assume that the amplitude in that region is EFT computable. We don't really need to assume anything else about it, just that it's computable in an EFT. So in particular, we don't really need to assume anything about the analytic structure of the amplitude in this region. And this is important in the case of gravity or whenever you have massless particles, because you could have some complicated series of branch cuts and singularities in this low energy region that aren't actually completely understood to arbitrary loop order. So we don't want to have to assume anything in particular about that. We just want to assume that the amplitude is EFT computable in this region. And then outside this EFT region, we have some cuts on the real axis. And furthermore, the discontinuity of the amplitude across these cuts is can be expressed in terms of the masses and three-point couplings of exchanged particles. And the real analyticity assumption that we're making is just that the amplitude is analytic in this region out here, the high energy region away from the cuts. Okay, but to be a little bit more precise, we have to write down something about the low energy amplitude. And the simplest assumption that you might make is that the theory is weakly coupled at low energies. So for example, we could, if you assume the theory is weakly coupled at low energies, then it should have some low energy expansion that looks like what you would get in a tree level EFT. And I just want to emphasize that this is sort of the simplest setup you could take. You could include loops in these kinds of bounds if you wanted to. And the point is just that the bounds that we get will be linear in the amplitude. And the effect of loops is basically just to create to make it so that there's a nonlinear map between the Lagrangian and the amplitude M. But the bounds are still linear in M. Okay. Okay, any questions about analyticity? Okay. All right, the next assumption is unitarity. And for us, this is just a statement that the amplitude has partial wave expansion, and the coefficients in this expansion have so the partial wave coefficients C sub j of s have a positive imaginary part, and actually the imaginary part is also bounded. It's between 0 and 2. This is a consequence of partial wave unitarity, and this it gives a bound basically on the discontinuity of the amplitude in the high energy region, and that's where the meat of the bounds at low energies are going to come from. So that's relatively simple. Let's see. I should comment here. So P sub j is a Legendre polynomial or a Geigenbauer polynomial in higher dimensions. And of course, if you have spinning particles, then it's a more general matrix element of the rotation group. Okay, good. So the last assumption is Reggie boundedness, and this is the most subtle one and the one that I want to spend some time talking about. So if you want to derive dispersive bounds that have G Newton in them, then you need to be able to write down spin-2 subtracted dispersion relations. So the idea with a dispersion relation is you take the amplitude, you divide by some factor. So this is called the subtraction, although it really should be called the division. So you divide by some factor and take a contour integral around infinity. And if the amplitude is sufficiently bounded at infinity, this contour integral vanishes. And then bringing the contour inside, you get a relation between high and low energy parts of the amplitude. Now, if you look at the contribution at low energies, then terms that grow like s to the k will contribute to the spin k subtracted sum rule. And if they grow at a slower rate, they won't contribute. So for example, gravity, the contribution of gravity, which grows like s squared to m low, doesn't contribute to spin 4 and higher subtracted sum rules. So in order to get something that depends on gravity, we need to include at least one spin 2 sum rule. And so the specific boundedness assumption that we'll make is that a spin 2 subtracted dispersion relation converges. So the condition on m is that this limit of m over s squared goes to 0 as s goes in any direction in the complex plane. And I'll explain this in a little bit, but we actually only need this boundedness assumption for a compact range of t between minus m squared and 0, where again, capital M is the UV cutoff of the theory. Okay, so the assumption that we're making is that a spin 2 dispersion relation converges, and that is really a necessary assumption in order to get something that has gravity in the answer. Okay, so why should we be making this assumption? So one comment is that this boundedness property is true in weakly coupled string theory. So in string theory, m grows like s to the 2 plus alpha prime t, and remember t is less than 0. So m grows at a slower rate than s squared. And this is a sufficient condition to make a spin 2 subtracted dispersion relation converge. Now, I should also say that there's something called the classical Reggie growth conjecture, which is that the amplitude grows, the rate of growth of the amplitude is less than or equal to s squared. And this conjecture has appeared in several places. There's a nice argument in this paper by Kems from 2014 explaining how this, giving a causality argument for this condition. And it's connected to the chaos bound of Maldacena, Schenker, and Stanford. And there was also recently a nice paper by this group from India arguing for this condition from ADS-CFT. And so there are lots of physical reasons to believe that the amplitude should not grow faster than s squared. But to write down a spin-to dispersion relation, you actually need something stronger than that. You need it to grow strictly less fast than s squared. So this is kind of what we really need is a kind of quantum Reggie growth condition. Right. So this condition, of course, is true in weakly coupled string theory. So if you use spin-to dispersion relations, you do derive true bounds on a weakly coupled string theory. But we'd like to understand whether this condition is really true and whether we should feel comfortable using it. So I want to talk a little bit more about that. Are there any questions before I continue?
So sorry, I have a question.
Yes.
If I know a UV theory, how can I calculate the amplitude at a high energy? You know, how to calculate the boundary of the dispersion relation?
How to calculate at the boundary of the integration region? Is that the question?
Yeah. Yeah.
Right. So the assumption that we're making is that the boundary of the integration region does not contribute. So we're writing down dispersion relations where the factor in the denominator.
Yes. Generally, if we look at the dimension 6 operator dispersion relation, the amplitude, you know, you need to know the high energy the m term that proportional to linear proportional to s. So how can I get the s term, not the s squared term? Actually, you know,
Sorry,
for dimension 6 operator, the boundary of the dispersion relation usually, you know, that vanish. So I want to know how can you determine the boundary?
Okay, I couldn't quite understand everything in your question, but I heard you mention dimension 6 operators. So the point here is that this Renyi boundedness means that the amplitude grows slower than what you would get from basically any irrelevant operator in the effective Lagrangian. So it's kind of like basically it means that these Wilson coefficients, you can't just dial them willy-nilly. So you can't just add to the amplitude some polynomial of s. That's not allowed. The amplitude has to decay to infinity, and that actually imposes strong conditions on the coefficients of those higher dimension operators. They have to fit together in a nice way to achieve this Reggie boundedness. I don't know if that answers your question. So the condition, this is kind of interesting. I mean, there's one assumption we're making about the amplitude, which is that it decays sufficiently fast at infinity, and that really places strong constraints on all of the irrelevant Wilson coefficients. So in particular, here, let me go back a little bit. So so the condition that we want to impose is that the amplitude decays sufficiently fast out here. So in the upper half plane somewhere, but in the high energy region. And this is not a condition that we're imposing in the low energy region. Like the amplitude in the low energy region could have some interesting behavior. And the cutoff on the EFT is here, right? So inside there is the region where you can use, you know, your perturbative calculations involving dimension 6 operators or whatever. The assumption we're making is about how the amplitude behaves outside that region.
So David, because Zoom is a little clumsy, it might just be better to hold questions until the end.
Okay, all right, that sounds good. So, but I should say, this is an assumption about something beyond the EFT regime. And so that in particular, in the case of gravity, it makes this a mysterious regime. So this is sort of why, this is part of why this is an interesting question. How should we think about this assumption?
Okay.
Right, so this is a mysterious regime. We don't know much about gravity in this regime beyond the UV cutoff of the low energy effective theory. So why should we assume something about how the amplitude behaves? So one comment is that spin-to dispersion relations are actually rigorously derivable in the context of ADS-CFT. And furthermore, they become this flat space spin 2 dispersion relation that I called C sub 2 comma T in an appropriate flat space limit. And the interesting thing about this argument is, first of all, it's a non-perturbative argument. You use non-perturbative conditions on CFTs. So this addresses the problem of high energy gravity being mysterious. You really know what you're working with, and you know that you have a non-perturbative theory of quantum gravity. This argument actually bypasses analyticity assumptions about the S matrix. So you don't actually construct the S matrix and prove things about its analyticity properties. You actually just go straight to a spin 2 dispersion relation. So the claim is that in a consistent theory of quantum gravity in ADS, spin 2 dispersion relations converge. And another interesting thing about the CFT calculation is that it actually only gives you the spin 2 dispersion relation in this compact range of T. So I would say that mystery still exists if you try to move outside this compact range of T. And we should be suspicious of trying to use spin 2 dispersion relations outside this range, or at least we don't really understand from the CFT point of view whether those make sense. And so we should also use caution in flat space. Okay, and this compact range of T is going to show up again a little bit later in the talk. So I wanted to make this comment that ADS CFT seems to imply that spin 2 dispersion relations make sense, but only for this limited range of T. Okay. Good. So I want to explain this a little bit more. So what is the observable that you look at in the case of ADS CFT? The idea is that you study a 4-point function, and this fact that spin 2 dispersion relations converge comes from studying the 4-point function in the Regge limit. So here's a picture. We have a 4-point function. We have 4 operator insertions. And to reach the Regge limit, you take 2 of the operators. Here I called them both V, and you boost them relative to the other 2 operators. And the boost parameter here is gamma. And schematically, a spin K dispersion relation in this context looks like some kind of integral against this 4-point function, an integral over the boost parameter. So it's some kind of integral d gamma of the 4-point function. It's really a double commutator. This plays the role of this is like the imaginary part of the amplitude. And then there's some kind of damping factor that depends on the spin K. And so you can see that at higher K, the damping factor works harder and harder and makes the integral more and more convergent. So the interesting thing in the context of CFT, the real meat that lets you use these dispersion relations is that this 4-point function is actually bounded in the Regge limit. So the physical picture of the 4-point function of this double commutator in the Regge limit is that as you start boosting it, initially you get a period of exponential growth. And this is the period that is relevant to the chaos bound for those of you who studied studied that paper. In a theory of gravity, there's this exponential growth with some maximal Lyapunov exponent, and in string theory, it's a submaximal Lyapunov exponent. But the point is that after this initial period of exponential growth, there's saturation, and this 4-point function is bounded in the Regge limit. So what this actually means is that a spin K dispersion relation of this type up here converges as long as K is bigger than 1. So the condition we actually need to write down a dispersion relation in this context is K bigger than 1. K equals 2 is definitely okay. We're not even close to the marginal case. The marginal case in ADS CFT is K equals 1. And I think this is kind of interesting. It means that if you could try to write down a K equals 1, a spin 1 dispersion relation in ADS CFT, and it would be true up to a boundary term at infinity. And it's interesting to ask if we can compute that boundary term. And I think it's also interesting to ask whether there could be a similar situation in flat space. So if you had a useful K equals 1 dispersion relation, it would give you much more information than the information I'm going to talk about in this talk, and much stronger bounds, and it would be really interesting to think about. So I wanted to point that out. So I guess there are 2 lessons that come from thinking about ADS-CFT. One is the fact that k equals 1 is the marginal case, and k equals 2 is definitely absolutely okay. We can have spin 2 dispersion relations. And the other is that the dispersion relations come with this compact range of t that we should remember. Okay. Any questions about that?
I have a
David?
question actually.
Yeah.
So you're saying that you can prove this bound for a finite range of t within ADS-CFT, but I'm just confused exactly about what do you mean by finite range of t, because I thought that this made sense in a flat space scattering amplitude.
Yeah. So
but you're in an ADS setup.
Yeah. So the thing that happens is here. Sorry. Let me scroll a little farther. So this is the statement of the spin 2 dispersion relation in flat space. So what happens in CFT is that you get an equality of this form, some low energy thing equals a high energy thing. And the high energy thing in the flat space limit becomes precisely this quantity, basically the contribution of a partial wave, but only if t is in the compact range. If t is outside that range, you get something that is not the contribution of a flat space partial wave. You actually get something different. So there is still a sum rule, but it's not a flat space dispersion relation. It has extra terms in the high energy contribution. And we actually haven't really looked at what those extra terms are very carefully. So there's still an equality, but it's modified. And maybe it would be interesting to look at what the flat space limit of this modified inequality is, what this modified equality is, whether it makes sense. But that's what happens. Does that answer the question?
Yeah, thank you.
Sorry, David, can I quickly follow up? So this happens in d larger than 4? Or where the flat space limit is infrared finite, or what happens in d equals 4?
So this particular effect, I think, doesn't really depend on d equals 4 or d bigger than 4. It happens in all dimensions. Because this is a question about the high energy contribution. So it's just a calculation involving a conformal block with large dimension.
But the whole sum rule, I mean, the whole sum rule, what happens to it in d equals 4? Because
okay, that's an interesting question. Let's leave that to the end.
Sorry.
Let's talk about d equals
Yes.
4 at the end. Yeah, that's a great question and an important one. Okay, good. So that's the end of the discussion of Reggie boundedness. So I would say that overall there are kind of two kinds of approaches to Reggie boundedness, and they're both complementary and interesting and worth thinking about more. One is thinking about causality and consistency conditions on the amplitude in the style of this Chems paper, and another is thinking about ADS-CFT, where you have a clear non-perturbative starting point. It would be great if we had other approaches to thinking about this problem. Okay, so what happens when you put all of these things together? You get relations between low and high energies. The idea of the dispersion relation is that you start with a contour integral around infinity, and then you pull the contour inside, and you can pick up contributions from either the high energy cuts here or the low energy region. So in the case, if you assume that the low energy theory is weakly coupled and you treat it at tree level, then the contribution from low energy is just some residues. And the sum rule that you get relates some low energy expansion where all the Wilson coefficients appear to
sorry, I still have a question. How about the big circle, the integration on the big circle? Generally it is done vanish. So you just look at the high dimension operator. That's right.
Sorry, I couldn't quite understand the integration on what?
On the big circle,
The big circle.
Yes.
Right. So the point is that we're assuming that the amplitude decays sufficiently fast that the integral on the big gray circle is 0.
But generally, I think for high dimension operator is fine, but for the low dimension operator,
So the point is that you
I
should
don't
not
think
be
so.
thinking about this big circle in terms of the low energy EFT. The big circle exists outside the low energy region. So you shouldn't be thinking about the contributions of individual Wilson coefficients to this big
Yes,
circle.
actually the Wilson coefficient is equal to the branch cut plus the integration on the big circle. This is the dispersion relation. Is that right? The Wilson coefficient actually is equal to the integration on the branch cut plus the integration on the big circle. Is that right? This is the
So yeah, the
EFT
Wilson
dispersion
coefficient
relation.
comes from the integral in the low energy region, and then you get an equality between Wilson coefficients and the high energy region.
Yes, plus the integration on the big circle.
Plus the integration on the big circle, which is 0.
Generally, for the low energy dimension, for the low dimension operator, it doesn't vanish. So
Maybe we
I
can
don't know. I just
follow-
want to know how can you deal with the boundary? Generally,
I think I've answered. I think I've answered your question for now. Maybe we can.
Yeah, the problem is, for people out there, the problem is the Zoom is clumsy, so it takes a long time to figure out exactly what you're asking. So
Okay.
it'd be much better to hold off to the end just because of Zoom. I apologize for the pandemic and Zoom.
Yeah, I have been inviting some questions, so
There's also very important the Slack channel.
right, there's a Slack channel. Okay, yeah, thank you. Okay. Good. So these are some examples of equalities that you get. So the first one is what you would get in the case of a scalar amplitude. This is a spin 2 subtracted dispersion relation. Here's a spin 4 dispersion relation. And I'm using this notation where an expectation value in these angle brackets is some kind of sum over high energy states. So we have a sum over high energy states of this unknown quantity here, rho sub j, which you may remember from unitarity is positive and bounded as well. Okay, so one thing that you can do with this is immediately recover or immediately see this result of Adams et al. That I mentioned at the beginning of the talk. You just take the spin 2 dispersion relation, and if you look at the case where you don't have gravity, so g equals 0, then you can take the forward limit, you set t equal to 0, and you get that 2g2 is some expectation value in a positive measure of a positive quantity, and therefore positive. So that's how their bound works. Okay, so now let's get to the case of gravity. So for gravity, you have this problem that if you try to take the forward limit of the spin 2 dispersion relation, then the low energy contribution blows up because of this T-channel pole. And I should say, let me back up just a little bit. So why are we taking the forward limit? So one point is that the idea of deriving these bounds is that you take a dispersion relation and you want to do some kind of manipulation on it so that on the right-hand side, you end up with the expectation value of a positive quantity in a positive measure. And the forward limit is a very natural way to get positive quantities on the right-hand side. So these are Gegenbauer polynomials. They oscillate as a function of the scattering angle. But if the scattering angle is 0, then the Gegenbauer polynomial is just 1. And so you automatically get something positive. So that's a very natural reason for looking at the forward limit. But the forward limit doesn't work in the case of gravity because of this problem from the T-channel pole. And it's useful to think about this problem in impact parameter space. So we can think of T as minus p squared, where p is the transverse momentum transfer. So p is the norm of p vector, where p vector is a d-2 dimensional vector. So this is parameterizing the transverse momentum. And the Fourier conjugate to p is b, the impact parameter. So let's look at what's happening in impact parameter space when we try to take the forward limit. So we can in general, think about taking the low energy part of the dispersion relation and integrating against some wave function of P. So this is one of the most general things that we can consider. We integrate against some function f of P. In impact parameter space, this looks like this. So we have f hat of B, which is basically the transverse Fourier transform of f. And this is what the contribution of gravity looks like in impact parameter space. And so the integral, in the case of the forward limit, basically what we're doing is we're taking f of P to be a delta function of P. We're setting P to 0. F hat of B then is 1. So what we're doing is taking the dispersion relation and we're convolving it with a wave function in impact parameter space that has support everywhere. It's just equal to 1. And so then it's easy to visualize what's happening in the integral. We have the contribution of gravity, which is this linearly growing thing, 8 pi g b. And in the forward limit, we're convolving it with a flat function. And so, of course, the answer is infinity. This also shows what we need to do to cure this infinity, which is that we shouldn't convolve with something that is just flat. We should convolve with something that decays. So we can consider an f hat of B that decays with B. And it doesn't have to decay exponentially. It just has to decay sufficiently fast so that its integral against gravity converges. And in practice, the types of f hats of B that you need to prove interesting things decay with some power law rate at large B. And another thing that I'm glossing over here, but that I'll explain in a moment, is that actually to prove dispersive bounds, f hat of B needs to be positive. So that's the other thing. That's the thing that tells you that you really need f hat of B to be localized in B. Now, if you can achieve this localization in impact parameter space, then it implies that the integral against gravity is finite. And in particular, if you can really localize f hat as small as possible, then that suppresses the contribution of gravity. And in order to write down some rules with the correct scaling from dimensional analysis, we want the contribution of gravity to go like 1 over m squared, right? Gravity has 8 pi g over p squared in its low energy sum rule. We want to basically replace p with capital M everywhere in order to get bounds that have the right dimensional analysis scaling. So we need to be able to suppress gravity so that its contribution looks like 1 over m squared. And that requires a wave packet f hat of B that is localized to within 1 over m. So this is what we need to look for. And the interesting thing is that you can actually find wave packets like this that are localized in B and still give positive contributions on the right-hand side of the dispersion relation. That's the thing that's maybe non-obvious from this analysis, but it turns out to be true. So, all right, so to localize this in impact parameter space, you really need high transverse momenta all the way up to this cutoff scale, capital M. And you might worry that the low energy effective theory expansion, the low energy expansion breaks down if we consider transverse momentum that's already at the cutoff scale. And there's a technical solution to this, which is to consider improved sum rules that make sense and have a controllable low energy contribution all the way from t equals 0 to t equals minus m squared. So you can write down improved sum rules by basically taking linear combinations of these dispersion relations. And the improved sum rules have this nice property that on the left-hand side, they have a finite sum of Wilson coefficients. And on the right-hand side is some known function. And these improved sum rules are valid, again, for this compact range of transverse momentum, p between 0 and m. So what we're looking for is some kind of wave function f of p that's localized in impact parameter space and compactly supported in momentum space. And furthermore, such that when we act with it on this dispersion relation, we get something positive on the right-hand side. Those are the 3 conditions that we need. So you search for this f of p. And if you can find an f of p such that the contribution of the heavy density is positive, then integrating the dispersion relation against f of p, you obtain an inequality on the low energy variables. And this positivity condition that you need on f actually implies positivity of f hat. So that's the thing that I glossed over before. Before we had some kind of integral of f hat of b against gravity, and I said that we really needed f hat of b to be localized. And the point is that f hat of b actually has to be positive, and that comes from this positivity condition, a particular limit of this positivity condition. Okay, so we have these conditions on f that we need in order to get a positivity condition, and these conditions basically replace the idea of expanding around the forward limit. So before I said that the forward limit is a really nice way to get something positive on the right-hand side because the Geigenbauers all just become constants. The claim is that there is an alternative way to get something positive, which is to look at these impact parameter localized functionals. You don't need to just take the forward limit. Okay, so you can do this, and it turns out these functions f of p exist. And in the case of 2-to-2 scalar scattering, you get bounds on Wilson coefficients that are valid in a theory of gravity. So here is an example such bound. So the axes here are, so there's G2. I know this is pretty small to read, and G3. So this is an exclusion plot in G2, G3 space. And the point is that these quantities appear with the factors of m and g expected from dimensional analysis and weak coupling. The claim on the plot is that the region to the right of these curves is allowed, and the region to the left is disallowed. One interesting consequence is that in a theory of gravity, G2 can actually be negative. It can be a little bit negative, but not too negative. And there's some nice physical intuition for this, which is that so this result in non-gravitational EFTs that G2 had to be positive, you can think of that as a consequence of causality. Basically, if you have a non-gravitational EFT and G2 is negative, then you would have some kind of time advance in scalar scattering. And the idea is that if you turn on gravity, then you can have a little bit of time advance from G2 because it'll be fixed by some kind of inherent time delay from gravity. That's the physical intuition. So that intuition, I think, is kind of useful for thinking about what these bounds should look like in different situations. So we can apply that we can apply that intuition in cases that aren't just scalar 2-to-2 scalar scattering, and the guess is that it should probably be true in these other cases as well. So there's there's like a technical numerical computation you have to do to get these bounds, but we should have some intuition for what the bounds should look like from that. Okay, and here's an example wave function f of p, just one that you can write down, and you can search for these f of p's numerically, and the numerical expressions are a little bit hard to interpret, but they at least satisfy all the positivity conditions necessary. And again, this is an integral over a compact range of p. 5 minutes. Okay, great. Yeah, I will definitely end on time. Okay, so one thing about this plot that is pretty glaringly obvious is that d equals 4 doesn't appear on it. And so I want to talk a little bit about that. I'll just say a few words. So there's a technical problem in d equals 4 with this approach, which is that the impact parameter amplitude for gravity actually diverges in d equals 4. And you could see that already in some of the expressions I wrote earlier in the talk. And it really comes from in the Fourier transform, you have some kind of d2p over p squared. This impact parameter amplitude diverges, basically the effect is that if you try to write down an f that satisfies all the positivity conditions that you want to make the right-hand side of the dispersion relation positive, then it will necessarily give infinity on the left-hand side. So you can't derive non-infinite bounds on the Wilson coefficients. So what you need to do to get something interesting is relax the conditions of positivity on F. So instead of requiring that the right-hand side is positive for everything that can possibly appear, you could allow the right-hand side to become a little bit negative. And if you allow the right-hand side to become a little bit negative, then you can write, then the left-hand side can become finite. If you do this, then you can get bounds in 4 dimensions, but they come with some kind of IR cutoff. So the idea is that you allow negativity at large impact parameters, and that negativity lets you write down finite bounds. So an example of such a bound is that in 4 dimensions, G2 is bounded below by this quantity, where we've imposed some kind of IR cutoff in Bmax in impact parameter space. I should say that in the context of ADS-CFT, this actually becomes a rigorous bound on theories in ADS4. And what happens is that Bmax naturally gets replaced with the ADS radius. And the idea is that gravity is diluted at distances longer than the ADS radius. And that cuts off the integral that would otherwise be infinity. This statement here on G2 in the case of 4 dimensions is not completely meaningless. It has a meaning in ADS, but the bound that you get has this extra log of capital M times R ADS in it. So the bound that you get is not consistent with what our first QFT professors told us we should assume about Wilson coefficients. It's worse than that, but it does exist. Right, and there are other problems with trying to apply these methods in 4 dimensions, which is that the amplitude itself is IR divergent when you include loops. So the basic observable that we're studying positivity of doesn't actually make sense in 4 dimensions in flat space. So I think there's some interesting questions here. One is how these loop level IR divergences in flat space are reflected in ADS. So the guess again is that there should be rigorous bounds on theories in ADS4, but there might be interesting non-trivial corrections due to loops because they're IR divergent in flat space. They could lead to interesting effects in ADS4, and those haven't been computed. I think it'd be interesting to think about that. But maybe a more interesting question for this conference is there a good IR safe observable in 4-dimensional flat space that we should be studying instead of the amplitude, where we can still write down some kind of spin-2 subtracted dispersion relation? Okay, so that's it. So I'll just conclude with this slide with some open questions. So the point, the physical point is that bounds on gravitational EFTs can come from spin-2 subtracted dispersion relations, where you look at wave functions with compact support in P and localized in B. And the expectation is that we can show that dimensional analysis is a theorem in gravity too. And so in this talk, I just talked about 2-scalar scattering, but the hope is that one could extend this to all parts of a gravitational EFT. And some intuition for the bounds that we expect is that the Wilson coefficients can give a little bit of time advance because that time advance is fixed by gravitational time delay. And I should say that this is, so I showed plots for scalar scattering, but one expects this to be true, for example, in Einstein-Maxwell theory for the F to the 4 term. So the F to the 4 term is positive in a non-gravitational theory, but I would expect that at least these kinds of dispersive bounds would allow it to be a little bit negative due to this effect. I think it's interesting to think about spin-1 subtracted dispersion relations, whether they can make sense and what the boundary term at infinity is, whether there are any reasonable physical assumptions we can make about it and what we could derive from that. And then the big question is, what observable should we be looking at in D = 4? And this is just a random comment, but in conformal field theory, the physical observables that are sort of nicest for thinking about these bounds are event shapes. And the idea is that a dispersion relation has an interpretation as being something about a commutativity of detectors in event shapes. And so I think it's interesting to ask whether we should be thinking about event shapes in flat space as well. So the idea is that if we have an amplitude, but we should think of two of the particles in the amplitude as actually being detectors living at null infinity. And that might be an interesting point of view to take and maybe worth exploring. So I'll stop there. Thanks.
Thank you. Questions? Yeah.
Can I ask, so in your T region, you had the condition that the amplitude was smaller than S squared. Can you get something a little more precise, like some S log to the KS or log S? Is it feasible to write something like that?
Yeah, that's a good question. So the question is how exactly M should behave at infinity. So let's see. So in ADS-CFT, I think the sharpest version of that is this saturation of the double commutator. So the claim is that the 4-point function is constant, is bounded by a constant in the Regge limit. And interpreting that in terms of an amplitude is, I'm not exactly sure what that gives in terms of an amplitude, but I would expect that it implies that these amplitudes integrated against, so if you integrate against a wave function in impact parameter spaces as we've been doing, and you look at the behavior in S, it implies that the amplitude should be bounded by a linear function of S. But yeah, I think that's the statement. Basically, the amplitude should be bounded by something that will make a k = 1 dispersion relation marginal.
Yeah, parts of this seem as though they should extend fairly naturally to higher point functions, and some of it is less obvious to me that it would extend. So really, it's a two-part question. Can you comment on that? And also whether you would even expect to get stronger bounds from higher point.
Yeah, so yeah, I can try to comment about that. So I think that this event shape point of view is a nice one to take for higher point amplitudes, because so the idea of the 4-point case is that you can think about having some kind of incoming state, and then you have two detectors like this and an outcoming state. And the dispersion relation, it can be phrased as basically commutativity of these two detectors. Like if one acts slightly before the other, and then you swap the order, those should be equal to each other. And that turns out to be equivalent to a dispersion relation. And so it gives a natural set of conditions that you could study in the higher point case, which is to just add more detectors. And look at the statement that all of these detectors commute with each other. And on the heavy contribution for this kind of observable comes from what happens if you act with the detector and you project onto intermediate heavy states that can appear, and then you act before you act with the other detector. So this also would generalize to the higher point case. You would have basically various intermediate heavy states, and then finally a light state at the end. And so this would, in terms of partial waves, this would be a partial wave in the comb channel, the so-called comb channel. So the diagram is that you take a 3-point coefficient, you take 3-point amplitudes and glue them like this. It's called a comb channel because it looks like a comb. So I think these are a natural set of inequalities to look at in the higher point case. I should say, though, that studying these numerically could be quite difficult because the heavy contributions are now not quadratic in the 3-point couplings. So basically, the the meat of all of this, the positivity is coming from the fact that this rho sub j here is quadratic in 3-point couplings. That's from the point of view of the partial wave expansion, that's why rho sub j is positive. And this quadraticness means you can turn this into a semi-definite program and solve it on a computer. But if you were to study observables like this, then you have something now that's quartic in 3-point couplings. And so you would have to study, you'd have to generalize semi-definite programming to work with quartic positivity conditions, which I think is, I don't think that's a solved problem in computer science at all. So technically, I think it could be quite challenging to compute like optimal bounds in this setup, but there could certainly be interesting bounds. So this is the most concrete thing I've thought about in this area, but I'm sure there's lots to say about higher point amplitudes, but I'll just make these comments.
Okay, let's thank David again.